In the last video, we looked at this new type of distribution, this chi-square distribution, which helped us determine how far an expected value and an observed value were in a qualitative data set. Not necessarily a quantitative, but now a qualitative. But not all data sets feature just one qualitative variable. In fact, we saw a lot of different examples where we were comparing two qualitative variables. And we're actually going to walk through an example we've seen before. And we want to say, is there any relationship between these two qualitative data sets? Specifically, are they independent of each other? Does one data set or does one variable impact the other qualitative variable? We've seen these before. We've seen these in something called a contingency table. We were able to convert these to joint probability tables, if you remember those. But that's what we're looking at here in this chi-square test for independence. Are two qualitative variables independent of each other? And they would prove to be independent if their expected values differed greatly from their observed values because of what was occurring. So let's jump in with a very common example, or an example that we've seen already, where we compared an age group to whether they would purchase a particular type of compression garment. So if you were under 35, will you be more inclined to buy Under Armour or Nike or Adidas or things like that? And the test for this, the hypothesis test, always ends up being the exact same. The null is always assuming that the two variables are independent. So this is always the same. The variables are independent. The alternative being that the variables are dependent. Whatever the variables are, that's who you would put in. So in this case here, we would say age and brand are independent, or age and brand are dependent. So we're trying to show whether your age is going to have an impact on what type of compression garment you might get. And just like with the other chi-squareds, we have to look at these observed values, and we have to compare them to what you would expect. And the way that we figure out the expected values is by first looking at the totals in the rows and columns. So we're going to add total to this row. We're going to add total. We're going to add total to this column. Total. We're going to add total. And I want to add up the rows and add up the columns. So 174 plus 54 is going to give us 228. And we add across 204. And we can do 168. And this is going to be 396 if we add across the column. So 174 plus 132 plus 90. And if we add across the second row, that's going to be 204. And that left us with a total of 600 patrons at this particular place. So how do you determine what you would expect? How many 35-year-olds would you expect there to be? Well, depending upon whatever row and column you're dealing with. So the ith row and the jth column, which is some pretty common notation. These are subscripts that highlight a row and column. You would take the row I total, so the row I total, multiply it by the column J total, so however many people were in that particular row, times how many people were in that particular column, and then divide it by the sample size. So for instance, if we were to do the under 35 and Under Armour, well, that's going to be the people in the first row and the first column. So we figure out how many people were in the first row total. First row is going to be these three values here, the under 35 row. So that's going to be 396. We multiply that by the number of people in the first column. So in the Under Armour column, that's 228. And then we divide that value by the total number of people in the sample. In this case here, there were 600. If you do all that out, you get 150.48. You would expect about 150 people who are under the age of 35 to purchase Under Armour. That's what you would expect. If you continue that calculation along the way, so let's do one more. Let's do Nike, which would be E12. So E12. So that's first row, second column. So first row featured 396 patrons. The second column was the Nike column, so you would expect 204 there. And then you would divide that by the total number of people, so 600. Multiply the numerator, divide by 600, and we would get a value of 134.64. 0.64. Sorry. 0.64. And hopefully your table's a little bit neater than mine. If you continue that pattern all the way down, so we would get for the next value for Adidas 110.88. Next value would be 77.52. So now we're into the second row, first column. This would be 69.36 and 57.12. So remember, these are the expected values. So you should expect that if you had, let's say, 600 people, of those 600 people, 150 of them would be under the age of 35 and would be choosing Under Armour. Or of those 600 people, you'd expect about 69 of them to be over 35 and choosing Nike. And what we're going to do is, just like we did with the last video, we're going to make the chi-square test statistic, and we're going to use that same formula of observed minus expected squared over the expected. So we're seeing how far are these expected values, how far are they differing from the values that we actually observed. So I'll show one and then assume that the rest will be the same. You can actually try out the calculation on your own. So let's do just the first one here. So under 35 and picking Under Armour. So we observed that 174 people did that. And actually, I'll give myself a little bit of space here, but noted that I'm doing this box here. 174 people were under 35 and chose Under Armour. But we would expect about 150 of them. We would expect about 150 of them of the 600. Okay, we take that number, we're going to square it, take the difference of it, square it, and then divide by the expected value. And we see that we get a value of 3.68. So 3.68. And again, it's sort of similar to standard deviation. You're seeing how far away really your expected value is from what you observed. All right, if we continue that calculation across the board, the Nike would end up being 0.05. Adidas would be 3.93. For over 35 and Under Armour, that would be 7.14, 0.10, and 7.63. And just like in the past, just like in the last video, we now can say that our chi-square statistic is equal to the sum of all of these. So we're going to add all of these up. The sum of all of those, oops, sorry, need a nicer sigma. The sum of all of those values ends up being 22.53. That's our test statistic. Now, you're probably then wondering, well, what are we going to actually compare this to? If we want to reject a null hypothesis here, we need some sort of alpha value. And let's say that alpha in this case is 0.05, just to stay consistent with what we've been doing. But we need to compare this to something. And we saw in the last video that chi-square also has a degree of freedom case. For these kinds of problems, for these contingency table problems, the degrees of freedom, and I'll make sure you do it in a brighter color so that we can see here, the degrees of freedom are actually going to equal the number of rows minus 1 times the number of columns minus 1. So it's almost like taking the degrees of freedom of the rows times the degrees of freedom of the columns. So in this case here, we had 2 rows, and then we had 3 columns. So we're looking at a distribution here with 2 times 1. So 2 minus 1 is 1, 3 minus 1 is 2, 1 times 2 is 2. So now if we look at a critical value to compare our test statistic to, we're looking at a chi-square with 2 degrees of freedom, and we're going to say the alpha value is 0.05. So our test statistic would be right there. that 5.991. Well, clearly, our test statistic of 22.53 is bigger than 5.991. So 22.53 is bigger than, that was 5.991. 5.991. So if we were to look at the distribution itself, here would be 5.991. That's our rejection region, and we can see that 22.53 is really in there. It's in the rejection region. So we can say that because it falls into that rejection region, that we can reject our null hypothesis. We're saying that if these were in fact completely independent variables, then the odds of this happening are so great that it seems like it can't even be possible. And because it's so unlikely, then we can reject the null hypothesis. It's very likely that it's not true. This data set wouldn't come about if the null were true. So because it's greater than our given critical value, we can reject the null hypothesis and accept the alternative hypothesis of that the variables are dependent upon each other. We can say that to some degree, the age is going to have an impact on what brand you're going to choose. It doesn't say one way or the other. It's just saying that there is some dependence in your age and what your brand of Under Armour is going to be. So you can make an inference based on that, but statistically we can just say that there is a dependence between these two things, that age is going to have some sort of influence on what brand you're going to choose from. And again, this is a major point in our statistics course, because this is now claiming whether there is some relationship between two qualitative variables. We've been looking at a lot of quantitative variables, and we're going to look at more quantitative variables and comparing two quantitative variables in a little bit. But this is our big test to determine if two qualitative variables in a contingency table are dependent or independent of each other. And it's done entirely through this chi-square distribution featuring comparing the observed values and the expected values.